Yes, good evening. This is group 19, and actually Jessica with my colleague, Apostle Rosemary. Currently, it's me, naturally Jessica. Our topic is contrastive self-supervised learning, and in our abstract, we have contrastive self-supervised learning, referring to a technique that allows us to train powerful model without the need for massive level datasets. Basically, this means that the contrastive learning, it's all about learning features without labeled data. Unlike unsupervised learning that uses unlabeled data, sorry. Then we shall have in this presentation, it will also include an extensive review of self-supervised methods that follow the contrastive approach. Commonly used pretext tasks, contrastive learning setup. Different architectures that have been proposed so far, and a review of contrastive learning-based methods, including SIM, CLR, MOCO, BIOL, SWAV, and SIMSIAM. And finally, we shall conclude with the limitations of the current methods and the need for further techniques and future directions to make meaningful progress. Then here, come to the introduction. The introduction, I'm talking about the supervised approach to learning features from labeled data. And this has almost reached its saturation due to intense labor required in manually annotating millions of data samples. And according to the introduction, we have the traditional supervised learning approaches, whereby these ones, they could rely heavily on the amount of annotated training data that could be available, unlike today. This is where self-supervised methods play a vital role in fueling the progress of deep learning without the need for expensive annotations, because those annotations of data samples, they used to be too expensive. So here comes in the self-supervised methods that can play a vital role in fueling the progress of deep learning without the need for those expensive annotations. Non-feature representations where data provide supervision, since it is self-supervised, whereby the data itself provide the supervision. The introduction continues, whereby here I'm talking about supervised learning. It not only depends on the expensive annotations, but it also faces some challenges or issues such as generalization error. This basically explains like the error that can affect the whole process. Yeah, the whole process. Then we have the spurious correlations and the adversarial attacks. Then still under introduction, let me talk about like recently the self-supervised learning methods have integrated both generative and contrastive approaches that have been able to utilize unlabeled data to learn the underlying representations. Remember, self-supervised uses unlabeled, like it can generally enable one to learn the general features without labeled data, meaning it uses the unlabeled one. Then a popular approach has been to propose various pretext tasks that help in learning features using the pseudo labels. Here, the tasks such as the pretext tasks. We have like image in painting, colorizing, grayscale images, jigsaw puzzles, super resolution, video frame prediction, audio visual correspondence, and others. And likely this has proven to be effective for learning good representations in self-supervised learning. Here, let me talk about contrastive learning. Like according to this image dataset, as you can see it, here, unlike generative models, contrastive learning is a discriminative approach that aims at grouping similar samples closer and diverse samples far from each other. Like here, as you can see, we have the original image. We have the original image. Then we have the augmented, whereby augmented can be transformed, like means the same as transformed. Then we have here, the explanation can be like, according to contrastive learning, the original image has got the augmented one, whereby the augmented one or the transformed one represents the positive image. Then the others, as you can see here, can represent the negative one, whereby the original one and the positive one can be like brought together in a similar way. Then all close. Then the original one and the negative one are sent far apart, as you can see in the diagram. Then continuing with the contrastive learning, we have the contrastive learning pipeline for self-supervised training. Here, as you can see, during training, the augmented version of the original sample is considered as the positive sample, like as we have seen in the previous one. Then, and the rest of the samples in the dataset are considered negative samples. Next, the model is trained in a way that it learns to differentiate positive samples from the negative ones. The differentiation is achieved with the help of some pretext tasks. Now, according to this diagram that shows the data set, the image data set, we have unlabeled images, as you can see, these ones. Then we have data augmentation. We have the encoder, pretext task, then contrastive learning as the process we are talking about. Here, you're going to find out that when the unlabeled image is transformed, and that transformation is carried out by the encoder, then you're going to realize that this one, like this image that I said, is explained under the pretext task, Then here, let me talk about the pretext tasks. Pretext tasks and the self-supervised tasks. These are tasks that can act as an important strategy to learn, like when one is learning representations of the data. But when one is learning those representations, one uses pseudo labels. Then these pseudo labels, like they are generated automatically based on the attributes found in the data. Then the learned model from the pretext task can be used for any downstream tasks such as classification, segmentation, detection. Then the next thing under pretext tasks can do that the mostly common used the mostly common used pretext tasks are divided into four main categories. The categories we have color transformation, we have geometric transformation, we have context-based task, and the cross-model based task. Basically, let me first talk about the color transformation. In color transformation, this one involves basic adjustments of color levels in an image, such as blurring, color distortion, converting, grayscale. Like here, when you look at these images, we have four, they are in four forms. We have the image in A, the image in B, the image in C, then in D. You're going to realize that during this pretext task, the network learns to recognize similar images invariant to their colors. Here, you're going to see that in A, the image is in its original form. Then in B, it's in Gaussian noise. Then C, it's in Gaussian blur. And in D, the color distortion, which is theta. So this one explains it color form, like as it just changes colors from its original to the Gaussian noise, the Gaussian blur, then the distortion, which is the theta. Then when it comes to the geometric transformation, we have a same, like we have one image, but in different forms. Here, in geometric transformation, there's spatial transformation. Like a geometric transformation is a spatial transformation where the geometry of the image is modified without altering its actual pixel information. Here, it's like the original image. It is just modified a bit without changing its original information. Then the transformations include scaling. We have random cropping, flipping, through which global to local view prediction is achieved. Like after modifying them, you achieve the global to local view. Here, you're going to see that in A, like A shows the original image. Then B, the image is crop and resize. It like shows half of it, but it resizes it. Those are compared to the original one. Then when it comes to C, the image is in its, let me say, it's in its original form, but again, it has just been rotated. Then D, crop, resize, and flip, whereby it is not all shown, it is resized. Then even its direction is a bit changed. And the context-based task, we have the jigsaw puzzle. Like we have an image here in A and an image, the same image in B. Then under the jigsaw puzzle, Traditionally, solving jigsaw puzzles has been a prominent task in learning features from an image in an unsupervised way, whereby this one involves identifying the correct position of the scrambled punches in an image by training an encoder, whereby this is all done by an encoder. And when you look at the images, you're going to see that in A, the image looks to be in its original form. Though, in terms of contrastive learning, the original image is the anchor and an augmented image formed by the scrambling, like as you can see in image B. The scrambling the patches in the original image acts as a positive sample. The augmented one or the transformed one acts as the positive sample. Then the rest of the images in the data set considered to be negative. As you can see, A shows the original image. Then B has some of the augmented image, and then others that are in the line of negative one. Remember, it's only the augmented or the transformed image that is positive. Then here we talk of the frame order based. In this approach, like it applies to data that extends to time. An ideal application would be the case of sensor data or a sequence of image frames. Like here, a video with shuffled order in the sequence of its image frames acts as a positive sample, while all the other videos that data set be the negative samples. Like as I explained, that the augmented ones are the ones in the positive side, then the remaining ones goes to the negative sample. Then, under future prediction, you're going to find out that the goal of a future prediction task is to predict high-level information of future time step given a series of past ones. Like here, when you're under contrastive learning, you have to first get all the past information about the task you're on. Then you can be able to find that, like to make the future predictions on it. After considering the past one, then a high dimensional data are compressed into a compact lower dimensional latent embedding space. Like, let me say, let me explain this. Let me say you have an image data set, as you can see. These ones can represent the past one, the series of past ones. Then making the future predictions. Of course, you have to first look at this one, but this one of the compressed into a compact lower dimensional latent embedding space. Like the powerful autoregressive models are used to summarize the information in the latent space. And the context latent representation city is produced as represented in a figure. Like, let me say, you have the series of the past ones. Remember, you have to use these ones to help you predict the future ones. But in the latent space, you have to compress, like to reduce Yeah, that is the end of my presentation. Let me call my colleague. Good evening, everyone. This is Rosemary, end of group 19. Let me continue from where my colleague ended from. Yeah, so the next thing in this place, we are going to talk about the encoders. And we say that these encoders play an integral role in any self-supervised learning pipeline as they are responsible for mapping the input samples to a latent space, like which reflects the role of an encoder in a self-supervised. Like, let me say, like, in the context of machine learning, especially deep learning, encoder refers to a component on a model that takes input, like take an example of an image, a text, or an audio, then transforms it into a meaningful representation, often called an embedding or a latent vector. For example, let's think of it like encoding information into different formats that the model can understand and work with. For example, we are seeing here, this is our encoder, this is our extracted future. Then this is the contrastive learning. So the gradient to be trained here, like is the encoder weight, and like when information is fed here, it transforms. Let me say this is our pretext task, the one my colleague discussed about. So for it, it transforms this pretext task into a downstream task. And my next slide, I'm going to explain to you about like this downstream tasks. Like these are tasks that are application specific, and they utilize the knowledge that was learned during the, let me say, the pretext task. Like here we have unlabeled data. So when this data is augmented and passed through an encoder, it becomes a pretext task. Then from there, we carry out this contrastive learning. Then when that data is fed, the image is dark, but there is a point here where we have knowledge, like knowledge transformation, whereby you find that, so at this point, after this data is being passed through this encoder, it converts it to be labeled data. So the next thing we are going to talk about, the existing models that are used in this contrastive self-supervised learning. So continuing with our presentation, the first model we have here is called the momentum contrast, also abbreviated as MOCO. So this MOCO mainly addresses two challenges, and the first one is how to make a large dynamic like how to make a large dynamic dictionary, maybe from small data sets. Then also how to make dynamic dictionary consistent when the encoder is being updated. So to have a large dictionary in contrastive self-supervised learning framework, like features in the previous batch, like we maintain them as a queue. So talking about this momentum contrast, it views like contrastive learning from a dictionary perspective to match a query with its positive key encoding and make it as like dissimilar as possible to the negative key encoding. Yeah, that's what mainly it does. So when it receives an input, like then it passes it through this momentum encoder. When you pass it through this normal encoder, it should be able to make like that data dissimilar from the first one. So then next on that, I sorry, I have the SIM R. So this one came up
with the idea of visual representation through contrast learning without like demanding a specific architecture or huge memory maybe about the previous record. Like, let me say, I say, like their proposed components, like their proposed framework consists of two main components. They're saying like their proposed framework consists of like following components, and the first one is we have the random augmented model, which discriminately transforms input data samples into like correlated view known as positive pairs. Then also they consist of a deep network encoder, which extracts, like as you can see here, which extracts like vector representation from data included like in an augmented version. Then they also have a multiple layer perception projection head from the representation like to the classification layer with the contrastive loss function. So the representation in this model like is learned by increasing the agreement between different augmented versions of the same data. Example, like via a contrastive loss, like sorry, in the latent space. So this model also introduces some interesting advancement, the contrastive self-supervised learning framework, which includes like, it involves using a larger batch size, larger models, like stronger data augmentations, adding multiple layer perceptions. Like we can see here, we can use the two encoders, like we have our two projectors, projection heads. Then also, it also exploits a deep projection along with like a memory mechanism. This other method we discussed about from Moko, as you can see. So next on that, I have the bootstrap your own latent, also abbreviated as BOY. Like the next model is bootstrap your own latent, also like abbreviated as BOY. We say that this BOY consists of two networks, namely an online network and a target network. Then like on a high level, this contrastive learning approach tries to get like rid of the necessary negative samples that are involved when doing the contrastive loss for a self-supervised learning. Then the two augmented views of the same image fed to the online and the target network respectively. As you can see, yeah, let me explain. So like we said that the two augmented views of the same image are fed to the online and the target network respectively. If this is our image, so the augmented form of that image is fed on both this online network and the target network. So a representation of the first view is learned using an encoder in this online network, and the updated learned weights are copied to the target network. So the first one that is fed here, after like making it augmented, it's then copied and fed again into this target, the target network as an exponential moving average, as you can see here. So the objective function like is simply can I say the minimization of the mean spot error like between the prediction from the online network and the target network. So these projection heads are used in the online network to reduce the dimensionality of the output of the encoder and also generate like a dimensional future for the predictor here. So the predictor is part of this online network which predicts the representation of the target network, like the data that was passed here and fed here. So this predictor here, its work is to predict the representation of this target network. So as you can see in this full architecture of the board, so like due to lack of symmetry between the online and the target network, we find that the moving average like learns to ignore these, can I say, the augmentation of the image, and what we get is the means code error of that image. So next on that, I have the simple Siamese, also abbreviated as SimSam, as our next model. Continuing with the SimSam model, we say that this Siamese network, like this SimSam model employs the Siamese network in contrastive learning. Like this SimSam architecture, it puts two augmentations of the same image and maximizes the similarities between them. Like if two images are fed here, then when they have some similarities, like let me take you up to this image. So when like it is fed in that SimSam model, we have here, we can see this image is similar to this one. So that model maximizes the similarities between this image. So here we can see that like the similarities between them is, let me say, maybe the size, the color. So that model like maximizes the similarities between two images. Or let me say this one, if they have some similarities, then it will maximize it. And coming back to that, yeah. So another thing on that, we say that like when like we also have our two identical encoders are used to process the augmented images. Then these identical encoders share the same weight, backbone, like which is like a rest net, and can I say the multi-layer perception. Then after one of the encoders, we have all of them having a projection, but then after one of the encoders, we have a predictor added to it, this, and the predictor function is to transform the output of the encoder and then matches it with the output of this other encoder, like then, and maximizes like the difference between them. Then like maybe despite its relative simple architecture, we say that when this SimSam is tested on 1,000 classes on the other ImageNet that is used like to predict their accuracy, see that it reaches a competitive results when compared to other state-of-art complex architectures, such as we have this previous one called Moko. So next on that, we have another model called swapping assignments between views, also abbreviated as swap. So this swap is a self-supervised method that exploits the contrastive method without the need for like pairwise comparison, and is therefore not like can I say a computationality expensive. So in a swap, we learn to predict the cluster assignment of one view, like from the representation of another view. Talking more about this swap model, like in this swap, we see that like we have the two augmented views of the same image. are fed into two feature encoders. Like we can have our augmented image here, they are fed into this encoder and like this one. So you see that these features are mapped to its nearest neighbor in a set maybe of clustered, which is a finite length discrete code book. Like. So this algorithm predicts the code of one view from the representation of another view, then swaps the prediction loss, and then given, like it swaps the prediction loss given and is calculated from the code like and the features of this thing. So next, leaving, going away from the models, like we have also the advantages, the importance of this self-supervised learning. We say that this self-supervised learning leverages the power of data without relying on the labeled data and learn those subtitle representations and patterns which are difficult for supervised model to learn. Like it doesn't need, when I say labeled data, it can get those unlabeled data, then extracts the characteristics between them and uses that data for many comparison, computations, all that. Then in addition to learning good representation, this self-supervised learning also like mitigates the problem costs involved in the process of annotating data. Remember all that those codes that will be involved like annotating data, extracting images, let me say shuffling image. So it reduces that in that for it, it can take in any type of the data, learns it, then extracts the characteristics in that data and uses it to perform a given task. Then this self-supervised learning also comes handy in dealing with all the formation problems in data labeling by mitigating like the resilience of class levels of that data. Like take an example of some, if it was a numeric data, let me say, like for example, we have the wine quality data set that comes like the data can have some null values, can have some outliers. So this self-supervised learning mitigates such resilience, the class levels of such data. Then away from that, it also has some limitations, and the first thing is this SSL method. For example, Mobileye does not capture the viewpoint and category instances like invariance, which is of important consideration in task. Then I say that SSL also is greatly dependent on the pretext task chosen for its training. So remember, we have the pretext task, then also the downstream task. So when it's going to perform a downstream task, it has to depend on that pretext task. So if that pretext task wasn't performed, it makes it difficult for it to perform this downstream task. Then last on that, we say in the SSL, like the representation not using the self-supervised objectives, which are like greatly influenced by the underlying data. And what are the underlying data? Those underlying characteristics that can be given in the data set that is being used. Like if we have this as our data set, like what are the underlying characteristics here is what we use. Then next on this, we also have the references for our work, and that marks the end of our presentation.